Welcome. Today we'll discuss about properties of functional dependencies. So we have the following properties: reflexivity property, transitivity, augmentation, union and decomposition. We can discuss one by one. So first one is reflexivity. So here if you see, so if B is a subset of A, okay, so it means B is a subset of A. Okay, so A is going to determine the B, right? So the functionally determines B. So A determines B. This means that any of the attributes trivially becomes their own subset. Okay. So this is a trivial dependency where the dependent attributes are already a part of the determinant. Okay, when we say A determines B, or when we say B is a subset of A, okay, so this is a trivial dependency where the dependent attributes are already a part of the determinant. Okay, so this property is called as reflexivity property or a trivial property. So we can see the example here. So here in this they have given employee ID and employee name. So employee ID and employee name is a set of attributes. Then employee ID comma employee name determines employee ID. Understood? So now this is A, okay, and this is B. Now if you see, B is a subset of this A. Okay, so employee ID is a subset of this employee ID comma employee name, which is a reflexive functional dependency, right? It means that it is a trivial dependency where this dependent attribute, that is the employee ID, is already a part of the determinant. Okay, we can see one more example for this. For example, if you have student ID comma student name, okay, so this determines student ID. So what is the meaning of this? So student ID is a subset of this student ID comma student name. Okay, so this is reflexive, or this is also called as a trivial dependency because this student ID, that is the dependent attribute student ID, is already a part of this determinant student ID comma name. Okay. So next property is augmentation property or augmentative property. So here if A is functionally determines B, okay, so A functionally determines B means A determines B, then AC functionally determines BC for any attributes C. Okay, it means that if you are adding any attribute to the determinant, right, so it doesn't invalidate the existing functional dependency. In more clear way, I will tell you. For example, if A is determining B, okay, and we can say C is another set of attribute. Okay, so A is determining B, so A is one attribute, B is one attribute. So A is determining B, and let us take C as another attribute. Okay, so then in this case AC functionally determines BC. This means by adding the attribute to both sides, okay, adding this attribute C to both sides of the functional dependency maintains the dependency. It is going to maintain the dependency. Okay, so this is the original functional dependency. For this, if I am adding the attribute C on both sides, okay, so the functional dependency maintains the dependency property. Okay, so again we can say AC is going to determine BC. So this is called as augmentation. So let us see with an example here. So employee ID is an attribute, employee name is an attribute. So employee ID determines the employee name. There if I add an attribute department to both sides, right? So employee ID comma department determines employee name comma department. Understood? So this is going to maintain the dependency. This functional dependency maintains the dependency. Okay, so that is why this is called as augmentation. If we see one more example for this, let us take the same student ID. Okay, student ID determines the student name. Okay, student ID is one attribute, student name is one attribute. So student ID determines student name is the existing functional dependency. So now let us take another attribute, course ID. Okay, so if I add this course ID on both the sides, okay, so student ID comma course ID determines student name comma course ID. Okay, so this means by adding this course ID to both the side of the functional dependency, this original functional dependency, it's going to maintain the dependency as it is. Okay, so this is called as augmentation property. And next is the transitivity property. So here, so if A functionally determines B, okay, so A functionally determines B, and if this B functionally determines C, then I can write A determines C. So this is called as transitivity dependency. Okay, it is an indirect dependency. Okay, so this transitivity property allows for the inference of indirect dependency. Okay, so it is allowing indirect dependencies. If you see with an example here, so employee ID is an attribute, department ID is an attribute. So employee ID is determining department ID and department ID is determining the department name. Okay, so employee ID is determining department ID and department ID is determining department name. Okay, so then we can say this employee ID can determine department name. So it is an indirect dependency. So if A determines B and if B determines C, I can simply say A can determine C. So employee ID can determine the department name. So this is transitive property. Okay, so next we'll move on to union property. So union property, so if X determines Y and X determines Z, then I can tell X determines both Y as well as Z. Okay, understood? So here the proof is X determines Y and X determines Z. So from the augmentation rule I can combine this. So X determines Y and X determines Z. Okay, so that is this. And by union property I can combine this as X determines Y, Z. So that is the union property. Okay, and next is the decomposition property. So if you see here, X determines YZ. So I can tell X can determine Y and X can determine Z. Decomposition, we are separating it. Okay, so X determines YZ implies that X can determine Y and X can determine Z. So this is the decomposition property. Okay, so now understood. So what are all the properties? reflexivity property, transitivity property, augmentation property, union, and decomposition. What is reflexive property? If A determines B, yes, so if A determines B, it means that any set of the attribute trivially becomes its own subset. For example, if I say A comma B determines A, okay, so this is its own subset, or I can say A comma B determines B. So this is my reflexivity property, or B determines B, A determines A. So it is its own subset. So that is called as your reflexivity property. And what is the next one? Augmentation property. What is augmentation property? If A determines B, and if I'm adding another attribute C on both sides, I can say AC determines BC. So this is augmentation property. And next is transitivity property. So what is transitivity property? If A determines B, right, and B determines C, I can say A determines C. Indirect dependency, that is transitivity. And next is union. So what is union? So if X determines Y and X determines Z, I can simply say X determines Y and Z. So this is union property. So what is decomposition property? So if X determines YZ, I can say X can determine Y and X can determine Z. So this is decomposition property. So reflexive property, augmentation property, transitivity property, then this is union property, and this is decomposition property. Okay, any doubt in this? Okay, so next we'll move to types of functional dependency. So we have the following types: trivial functional dependency, non-trivial functional dependency, multi-value dependency, transitivity dependency, full functional, and partial dependency. We can discuss one by one. So this one we have already seen in the reflexive property, the same thing. So in trivial functional dependency, a dependent is always a subset of determinants. So if A determines B, B is always a subset of A. So that is the trivial dependency. Otherwise we can say this right hand side is a subset of this left hand side. Okay, right? So X determine Y is a trivial functional dependency if Y is a subset of A. Okay, and A determines A, or B determines, for example, if A determines B is a trivial functional dependency, here B is a subset of A. Okay, and also we can say A can determine A or B can determine B. So these are also trivial. It is also true, always true, and adds no, because it is true because it doesn't add any new information, right? So this is also a trivial dependency only. We see an example here. So A, B, C. So A, B, C can determine A, B, or it can determine A, or it can determine itself A, B, C. Okay. So this is called as a trivial functional dependency. Then another example, roll number and name are two attributes. Roll number and name can determine name is a trivial functional dependency because this dependent is a subset of this determinant. And also roll number can determine itself. Roll number can determine roll number itself. This is also a trivial functional dependency only. It is always true because it doesn't add any new information. Okay, so that is trivial functional dependency. So trivial functional dependency means the determinant should be the subset of dependent should be the subset of determinant. Okay, and next is a non-trivial dependency. Non-trivial dependency means it should not be the subset of the determinant. Non-trivial functional dependency, the dependent is strictly not the subset of the determinant. Okay, so if x determines y, y should not be the subset of x. Then it is called as non-trivial dependency. Okay, that is this right hand side is not a subset. Right hand side is not a subset of this left hand side. You can see an example here. So ID determines name, right? And name determines date of birth. Okay, and here if you see here, roll number comma name determines age. So age is not a subset of these two. So date of birth is not a subset of this. Name is not a subset of ID. So this functional dependency is a non-trivial functional dependency. Whereas in trivial dependency, if you take this example, roll number comma name comma age determines age. If you say this, age is a dependent, right? And this is the determinant. So age is a functional dependency of this set, right? So this is trivial. If I say roll number name determines age, so age is not a subset of this. So this is non-trivial. Got it? Fine. Next we'll move to multivariate functional dependency. So in a multivariate functional dependency, the entities of dependent set, you can see here, entities of dependent set are not dependent on each other. So here they have given example. If A determines B comma C, this B comma C are not dependent on each other. Okay, so that there doesn't exist the functional dependency between this B and C. Then that is called as multivariate functional dependency. Okay, there should not be any dependency between these two. Okay, so for example, they have given bike model determines the color and manufacture. Okay, so what is the multivariate functional dependency? These two, there should not be any functional dependency between these two. Okay, so here if you see, the color do not depend upon the manufacturing year, and the manufacturing year does not depend upon the color. So they are independent of each other. Only the color and the manufacturing year is linked to the bike model, right? So these two are independent. So that's why this is called as a multivariate functional dependency. Okay, so this color doesn't depend upon the manufacturing year, or this manufacturing year doesn't depend upon the color. So both are independent. Right? So this is called as a multivariate functional dependency. And next is the transitive functional dependency. So we know this transitive property, no? So if A determines B and B determines C, I can say A determines C. That's the same thing. Okay, so in a transitive functional dependency, the dependent is indirectly dependent on the determinant. Okay, so this dependent is indirectly dependent on the determinant. So if you see in this relation, so enrollment number determines the department and department determines the building number. So I can say enrollment number can determine the building, right? It is indirect. Okay, so hence it is a transitive functional dependency. Next we can go for fully functional dependency. So here in a full functional dependency, an attribute or a set of attribute uniquely determines another attribute or a set of attributes. If a relation R has an attribute x, y, z with the dependency x determines y and x determines z, which states that those dependencies are fully functional provided the non-key attributes depends on the entire composite key. What is the meaning of this? So the non-key attribute is a functional dependent on entire composite key. It is not just a part of it. It is an depending on the entire composite. For example, if you take in this example, so A, B, C. So in the relation A, B, C with the composite key A, B. Okay. So this key depends entirely on this. Okay, so this depends entirely on this, or we can say the functional dependency, this A comma B determines C. If I say this, it is a combined one. A comma B cannot be separated because it is entirely depending, right? So removing this A or B, it will break the dependency. So the non-key attributes, okay, so the non-key attribute is functional dependent on the entire composite key, right? So that is fully functional. I can simply say like the non-key attribute is functionally dependent on entire composite candidate key. That is, it is not a part of, it is not just a not just a part of it. Okay, actually this is the requirement of your second norm. Okay, so we'll move on to the next one. So partial functional dependency. So partial functional dependency, a non-key attribute depends on a part of a composite key. Depends on a part of a composite key rather than the whole key. So in a relation R, if you have the attribute x, y, z, x and y are the composite key and z is the non-composite attribute. So then x determines z is a partial function. Okay, so if I say if z depends on both x and y means then that is your fully dependent. So here Z depends only on the X, not on the Y. So it is a part of the composite key. Okay, so it is depending only on a part of a composite key, only on X. So that is called as a partial functional dependency. Understood? So X, Y and Z are the attributes, right? And XY is the composite key and Z is a non-attribute, non-key. Okay, non-key attribute. So this is the composite attribute and this is the non-key attribute. So here if I say this X is a functional dependency of Z, it means that so Z depends only on X, not on both X and Y, whereas this is your partial functional dependency, whereas in your fully dependence X and Y is a composite key and Z is a non-key attribute, means Z should depend both on X and Y, complete composite key. You cannot separate X and Y separately. Okay, so Z should be dependent on both X and Y. It cannot be separated. This X and Y, this composite cannot be separated in a full. In partial it is separated. It depends only on the X, a part of this composite key. So X and Y is a composite key. Z is a non-key. So this non-key attribute depends upon a part of the composite key, that is partial functional dependency. Here if you see, Z is a non-key attribute and X and Y is the composite key. So this non-key attribute should completely depend upon this whole composite key. This X and Y cannot be separated. So that is fully functional and this is partial. Okay, so you understood? So the different types. So first one was the trivial. So what is trivial dependency? So trivial dependency, if A determine B is a trivial dependency, then B should be the subset of A. B should be the subset of A. Okay, and also we can say A can determine A or B can determine B. So this is my trivial. And in non-trivial, if I say A determines B, B should not be the subset of A. So that is the non-trivial. Multivalid means if A determines B comma C, this B and C should be independent of each other. Okay, it should be independent. That is multivalid functional dependency. Transitivity dependency, if A determines B and B determines C, then I can say A determines C. So that is transitive dependency. And your fully functional dependency, if I say A comma B determines C and C is a non-key attribute and AB is a composite attribute, so this C should be completely dependent on this AB. This A and B cannot be separated, that is fully functional dependency. And if I say A comma B is a functional dependency of C, I can tell this A can determine C. So it means the C is dependent only a part of the composite key. So this is a partial functional dependency. Thank you.